Hey everyone, in this video we're going to be looking at right triangle trigonometry. Whether this is the first time that we're seeing it or if we've seen this before in geometry, we're coming back and revisiting it here again. So where trigonometry really came from, or where it was founded on, what it was founded on, the mathematician noticed that if we have similar right triangles, so a right angle and say a congruent angle, that all of the different triangles with those angle measures, they noticed that there was a common ratio. So if I were to divide the longest leg by the shortest leg, we would always get the same ratio regardless of what the numbers were, as long as the angles were congruent. So if I were to, I'm going to show you this here. I have these four triangles and I have this one that's kind of empty. If I were to take, say, 30 and divide it by 50, okay, I get 0.6. So if I were to do the same thing here, the shorter leg, 33 and divide it by 55, we get 0.6. If I come here and 15 divided by 25, we get 0.6 again. And if I take 21 and divide it by 35, we get 0.6 again. Now, we're not always going to get 0.6 when we divide those two legs. It's just when the angle measures 31, the shortest leg divided by the other leg will give us 0.6. And that observation really is where trigonometry is founded, with right triangles. Before we go any further, we really don't want to talk about or say shortest leg, longest leg, and yes, we actually have terms for how we talk about the right triangles. So, let's say we had, do this here. Okay, so first thing is this little symbol represents theta. This we are going to call our reference angle. And again, you say it's theta. So we know the hypotenuse is the side across from the right angle. How we name these two, so the hypotenuse and another leg will form your reference angle. So this reference angle is formed by the hypotenuse and the side we call the adjacent. So the adjacent and the hypotenuse will always form our reference angle. And the one that remains, we're going to call the opposite. Now, it's going to get annoying if we were to write hypotenuse, adjacent, opposite every single time. So we're going to abbreviate these HYP, or just H, and then ADJ, or just A, and then OPP, or just O. All right? So we're going to use this terminology: reference angle, opposite, adjacent, hypotenuse. So notice how I went about identifying. I identified the hypotenuse, then I identified the adjacent, and the remaining side is the opposite. The purpose of trig is this is going to eventually help us find angle measures and side lengths. And notice this triangle here that only has one leg. Well, you're thinking, well, if these are similar triangles, couldn't we set up a proportion and find this unknown leg? And you would be actually correct in thinking that. But what if you did not know any other triangle? So you only had this one. You would not be able to set up a proportion in that sense. And that's where trigonometry is going to lead us to. If you recall, if you remember from the geometry skills that you were taught. Now, so looking at this, the names we give to certain ratios. So when here I was dividing shortest leg by the longer leg, we actually are going to put names to them. So we have three what we call basic trig functions. or ratios. All right, so we have sine of our reference angle, which we abbreviate just SIN, and this is going to be the opposite over hypotenuse. Always. Take the opposite leg divided by the hypotenuse. That value is the sine of the angle. And then we have cosine. And then we have just COS of our reference angle, and that's going to be adjacent over hypotenuse. Again, same thing, a decimal value. That decimal value is considered cosine. And then we have tangent of our reference angle, or just TAN. We still say tangent. This is opposite over adjacent. All right. Now there is a mnemonic device that can help you memorize the ratios. There's two versions of it. Okay, so as I wrote this out, sine opposite hypotenuse, cosine adjacent hypotenuse, tangent opposite adjacent. And it's really the same thing here, just put it in a different order. So when you say this, we say this one is pronounced SOHCAHTOA, but in my opinion, when I say that, it sounds a lot like you're saying sucking a toe. And I'm not really into that kind of thing. I mean, you might be, so you could use that SOHCAHTOA. I won't judge you at all, but I like the sound of the second one, Toa Soka. Just it flows out of the mouth. Toa Soka. So there's two ways of remembering this. So those are three of the three basic trig functions. There are three additional. We call these the reciprocal trig ratios. So the three are cosecant of our reference angle, which we abbreviate CSC, but still say cosecant. This is the reciprocal of sine, so it means 1 over sine. So if sine was opposite over hypotenuse, this would become hypotenuse over opposite. And then we have secant of our reference angle. Secant we spell SEC, still saying secant. This is the reciprocal of cosine, which would make it hypotenuse over adjacent. And then we have cotangent, and you could probably imagine already what this is the reciprocal of, well, tangent. So that would make it adjacent over opposite. So we have these. Now using these, let's actually examine a triangle and write the ratios for our reference angle. So let's say we have this figure. Okay. In a problem, you will always know where the reference angle is. Okay, whether you're given the angle measure of the angle or theta to mark where the reference angle is. That's very important, because without that reference angle, we would not know which side's the adjacent and which side's the opposite. So let's begin. Before we write the ratios, I want us to identify what sides are which. So the hypotenuse is the quickest and easiest one to identify. Right angle, there it is. The other side that forms our reference angle, so it'll be this side, this will be our adjacent. And then the remaining side is our opposite. All right, so let's go ahead and write our 6 trig ratios down. Sine of theta, so that was opposite over hypotenuse. That is 15 over 7. And we can go ahead and go ahead and do the reciprocal. Cosecant, which was hypotenuse over opposite. So that would be 17 over 15. And then we have cosine, adjacent over hypotenuse, therefore it's going to be 8 over 17. And it's reciprocal, secant, hypotenuse over adjacent, 17 over 8. leaving us with tangent, opposite over adjacent, 15 over 8, and then its reciprocal, 8 over 15. And it's, that simple. Notice I could not do this if I were not to label, or at least know what the adjacent side and opposite side, what they are. And an example for us to try is, this is a common example when we become familiar with the trig ratios, is let's let theta be an acute angle. Okay? And so let's assume that sine of our reference angle is 5 over 6. Evaluate the remaining trigonometric ratios. So how I'm going with this, based off of this only fraction, we need to get the other 6. So let's think of what we have. So sine of theta, that is opposite over hypotenuse. Okay, so that's what we have. So if I were to create myself a diagram just for my sake, I'd say let's put our reference angle there. The opposite to the reference angle would be 5. The hypotenuse would be 6. Okay, well, that's good. And I notice that we have a side that's empty. We don't know the adjacent. And we can actually find it. So here in this problem, we're going to use the Pythagorean theorem to find this unknown side. So that the Pythagorean theorem would give us 6 squared equals 5 squared plus the adjacent squared, 36 and 25. Solving this, you subtract 25 and then take the square root. We get that our adjacent is the square root of 11. Nice. So with that, so I'm going to put the square root of 11 right here. We can write all of our ratios down. So sine of theta, we know, 5 over 6. Cosine of theta, we now know, adjacent, hypotenuse, square root of 11 over 6. Tangent of theta, we know to be opposite, which was our 5, over adjacent. And then we have cosecant, and then secant, which is a reciprocal of cosine, so 6 over the square root of 11, and then cotangent, which will be the square root of 11 over 5. So the key to entering this problem, as I like to say it, is we have to use the Pythagorean theorem to find our third side in order to write any other trig ratio. We could have, based off sine, we could have immediately have written the cosecant ratio, but we could have gotten no further without using the Pythagorean theorem. All right, so writing ratios and identifying the sides. So let's actually talk for a brief moment before we close here about evaluating trig ratios with the calculator. All right, so something you should know is our graphing calculator, by default, so if you were to reset your graphing calculator, by default, it is going to be in degree mode, meaning it's going to look for the angle measures that you're using. It's going to think that the angle measures are in degrees, and we've talked previously about having degrees and then radians. So we'll talk what to do if we're using angle measures within radians, but its default is degree, okay? So let's say we have tangent of 17.25 degrees. So what we're going to find is back to our very beginning when our angle was 31. We got the same decimal for the ratio that we were doing. What we're saying here is if the angle was 17.25, regardless of the size of the triangle, if I were to divide the opposite by the adjacent with this angle measure, I would always get this one value. Okay, so if I were to take tangent, we have the 3 right here, tangent 17.25, 0.305. So it's approximately 0.3105. So every time I would divide opposite by adjacent with this angle measure, we would get this value. It doesn't tell us what the lengths are, it just tells us what the two sides would divide to. Let's try another. So the cosine of 32 degrees, 15 seconds, and 15 minutes, and 22 seconds. You're like, whoa, stop, halt, what are you doing? Well, I mean, we have degrees, we have decimal degrees, and we have degrees, minutes, and seconds. And you're thinking, well, could I convert this to decimal degree and then just do that? Of course you could, but there is actually a way to use this, and there's a way to recognize the degrees, minutes, and seconds. So let me walk you through that. So cosine of 32, and since we're having minutes and seconds, I need a degree symbol. So the degree symbol can be found under, if you look right above the apps button, see where it says angle? So I'm gonna hit second, apps, right there's our degree symbol, okay? Then 15, our seconds, same spot is in the angle measure. So second, apps, it's option 2. Now you would think, shouldn't the seconds be in the angle measure? It's for whatever reason, it's not. So the seconds symbol is over here by the plus sign, right beside where it says mem. So here I would have to hit, since it's in green, I have to hit alpha plus, so there's a second symbol, and enter, and it recognizes it. So 0.8457. So it's doing this again for you. The degrees and the minutes can be found in second app. Okay. The seconds symbol, you have to hit alpha and then the plus sign. So this is only needed if our angle measure is in degrees, minutes, and seconds. Okay, but there's nothing wrong with converting this to decimal degree and then using that. There's nothing wrong with that. Okay, so another example. Let's say if you have cosecant of just 16 degrees. Okay, well, cosecant's not here, nor do we see secant or cotangent. That's an issue. But what if I use my knowledge that this is the reciprocal of sine? I think I can do that. So 1 sine of 16. Hey, it did it for me. 3.6280 with rounding. Okay, not bad, right? So this is in degree. So then if we look at radians, how does that change the problem? So sine of, let's say, pi over 12. Could I convert radians to degrees and do that? Most definitely, sure, why not? that can be done. But if we go to our mode, and notice third or fourth line down, we see radians. And in geometry, you're probably wondering why, like, what is this radians? We now know what a radian is, and you were always frustrated because the calculator converted back to radians. It was annoying because you had to make sure it was in degrees. We're actually going to use radians now. So we can convert it to radians, and then I do sine of pi divided by 12. So now it's recognizing the angle measure, that this is an angle measure, 0.2588. Let's just try another. Cotangent of 3 pi over 4. So cotangent, I know this is 1 over tangent. Okay, so 1, and then tangent of 3 pi divided by 4, and we get exactly -1. Okay, so in this video, we've gone over what the trig ratios are. We've gone how to identify the trig ratios, and we're ending here with evaluating these ratios using our graphing calculator. We're going to continue on here with trigonometry. So in the next video, we're going to explore this some more.